All right, I have a couple of goals with this Excel workbook. I want to explore the topic of sampling distributions of statistics. So I want to actually create 3 different sampling distributions, which is very quick with Excel, and explore the further the relationship between the sampling distributions and this idea of biased versus unbiased estimators of population parameters. So I have a small population of data here on the left. There's 4 numbers, 24, 23, 12, and 19. And I want to take every possible sample of size 2 with replacement. And once I exhaust all possible samples, um, to actually create the distribution of sample statistics. So I have four values in the population. These numbers came from this, hypothetically, I just made those numbers up, but they came from this activity of asking 4 people their birthday, month and year, and then, for example, if your birthday is 8/1984, you would add up the 4 digits, 0, 8, 8, and 4, add up to 20. So here's just four values, and if I sample, there's going to be 16 possible samples because I have 4 options for the first choice and 4 options for the second. 4 times 4 is 16. So I'll go through this pretty quickly. The number 24 will be followed by one of 4 values. The 24 could be followed by a 24. It could be followed by a 23, a 12, or a 19. Same is true for the 23. 23 can be followed by any one of these 4, so I could just copy that down. Actually, just repeat this pattern. So first value can be followed by any one of the other 4 values, or any one of the 4 values. And the last number, 19, could be followed by the 24, 23, 12, or 19. Okay, so however you do it, exhaust all possible samples of size 2. So what I want to do is construct a sampling distribution of the mean, of the standard deviation, and of the variance. And then find the average value of all the sample means, the average value of all the sample standard deviations, and the average value of all the sample variances. And compare these results, these average of the sample statistics, compare those to the population parameters. So let's get the population parameters for the mean. So we'll do average of B2 through B5. There's the mean. Standard deviation, now remember this is a population, so we do stdev dot p for population. Oops, sorry, I forgot my equal sign. I think I do pretty often. So that's B2 to B5. Okay, so there's our sample standard deviation, or our population standard deviation. And our population variance, the function is VAR for variance, and we want VAR.P for variance of the population. And we'll use these 4 values. Okay, so now I have my population parameters. I want to calculate the individual sample means. So we could say equal average of these 2 numbers to the left. So if you could do 1 sample mean, you could do 100 very quickly with Excel. I will just copy this formula down. So these are our 16 individual x bars, our individual sample means. And we could calculate our sample standard deviations. So it's stdev dot s. Make sure it's dot s because it's a sample. And we're taking the standard deviation of these 2 numbers. There's no variation between them, so of course the standard deviation will be 0. All right, so let's copy this down. And then our sample variance, so equal var dot s for variance of the sample. And we want the variance of these two guys. Again, this should give us 0. And we can copy this down. Okay, so that's 48 individual calculations, 16 means, 16 standard deviations, 16 variances. And I did all 48 calculations in about a minute, less than a minute, maybe 40 seconds. So again, when you're doing any repetition in your calculations, Excel is very, very useful. Okay, so now I want to find the average of the means, the average of the standard deviations, and the average of the variances. Okay, so there's 19.5. Let's round it to one more place just so it looks the same. So our population mean is 19.5. This is the mean of the sample means. This is mu sub x bar, the average of the averages. So the sample mean, we say the sample mean is unbiased because the sample means target the population mean. So if I get rid of some of those sample means, we're close to the sample or to the population mean. The more sample means you have, the closer you should be to the population mean. Standard deviation. So let's look at the average value of all of those sample standard deviations. Okay, so the average of those 16 standard deviations, well, that's 3.54. So this should always underestimate the value of sigma, or the population standard deviation. But for the variance, let's see what happens. Equal variance, oh no, sorry, equal average of all of these variances. And we get 22.25. So you can see the means target the population mean, the variances target the population variance. So the mean and the variance are unbiased estimators. The standard deviation is what's called a biased estimator, because if you resample to exhaustion, all those sample standard deviations will not give you the same value as the population standard deviation. Okay, let me get rid of this. So this is our mu sub x bar. This is the mean of the sample means. Okay, the second thing I want to do here is apply the central limit theorem. So in this example, you'll see I have two problems, both having to do with the height of a randomly selected adult male or a group of randomly selected adult males. I spelled that wrong as an extra S. Okay. So you're given population mean and you're given population standard deviation. That means we're using the normal distribution z-scores. So the first question is find the probability that one randomly selected male is over 6 feet tall. That's 72 inches. And we know that the heights are normally distributed with a mean of 69.2. So this is what we did in the previous topic. The probability that one male is over 72 inches is going to be, well, the area to the right of 72. So this area to the right of 72 is going to be the probability that one randomly selected X value, or one randomly selected adult male, is over 72 inches. Now, here, In this second problem, we're saying, what is the probability that a sample of 20 adult males has an average height of over 6 feet tall? Okay, well, we saw that the sample means are the distribution of adult males, of heights of adult males, is normally distributed. So for any sample size, the distribution of sample means will also be normally distributed, with the mean equal to the population mean. So up here, these are x values. Down here, these are sample statistics. So same thing though. If we want the probability that the sample statistic, the x bar, is larger than 72 inches, well, still, it's the area to the right of 72. I didn't really draw these two to scale. If I did, this lower one would be a lot skinnier and tighter packed, or more tightly packed. The only difference between these two problems is how we calculate the z-score. So we have our formula for the z-score, x minus the mean divided by the standard deviation, for one randomly selected adult male. Or we have this from the central limit theorem, the z-score for a sample of adult males. So that's the only difference, the way we calculate the z-score. So let's come down here. So our population mean is 69.2 in both cases. Our population standard deviation is 2.9 in both cases. Our x value is 72. Again, 72 in both cases. So in problem 1, we want the probability that x is greater than 72, a single x value. In problem 2, we want the probability that an entire sample of 20 men has an average height larger than 72. So again, this is the only difference here, how we calculate the z-scores. So in this first case, I'm using, let's get rid of that, and let's get rid of that. X minus the mean divided by the standard deviation. So let's say that equals x minus mean divided by standard deviation. So the area to the right of 0.97, approximately 0.97. Over here, the z-score is going to be x bar, which is 72, minus the population mean, close parentheses, divided by sigma over the square root of n. That's equal to, over parentheses, sigma divided by the square root of 20. Okay, so I'm just plugging in, what's happening? Oh, I needed SART, not SQRT, square root of 20. There we go. And this is what we would expect, a much larger z-score, because it's much more unlikely to happen that, okay, one adult male is above average. That's not unlikely at all. But an entire group of 20, on average, being above 6 feet tall, well, that's highly unlikely. Either way, once we have our z-score, we calculate the same way. We're looking for the area to the right of a z-score. the x equals 72 and the x bar equals 72. They just have different z-scores, that's all. So we'll use Excel to do area to the left, and 1 minus area to the left is area to the right. So let's say equals 1 minus area to the left. So that's norm.s.dist. And here's our z-score. And always comma 1 for cumulative. So about a 16.7%, 17% chance of seeing the next randomly selected adult male is over 6 feet tall. It's not too unlikely. But the probability that the next group of 20 on average has an average between the group of 6 feet or taller than 6 feet tall. Well, let's see, that will be 1 minus norm.s.distribution, and here's the z-score. So 0.0000788. So a much, much lower probability. And this is what we would expect, because we expect a high likelihood of deviation from average for individual values, but as sample size goes up, variability goes down. And that's what we see over here on the right. Sample size goes up from 1 to 20, so the variability goes down. All right, that about does it for this one. I posted on the solutions to this Excel file, I posted some more information here in red text about the biased versus unbiased estimator. So please have a look at that. And otherwise, that does it for this one.